Humans have known about crystals for hundreds of years, but the scientific study of them didn't begin until the 1600s. A crystal is a solid with its atoms arranged in a highly ordered, repeating pattern. The smallest geometry that retains the crystal's overall symmetry is called a unit cell. In 1894, William Barlow proposed the structure of crystal symmetries, but there was no way to experimentally confirm them, yet. X-rays were discovered in 1895 by Wilhelm Röntgen. They make up the portion of the electromagnetic spectrum from 10 picometers to 10 nanometers. However, most have a wavelength of 0.1 to 1 nanometers. At first, they were thought of as electromagnetic waves, especially because single-slit experiments were able to determine their wavelength. After the proposal of the photon by Albert Einstein in 1905, it was suggested that X-rays could have wave and particle-like properties just as light does. However, this wasn't confirmed until 1922, when Arthur Compton showed that X-rays could be scattered by electrons. Meanwhile, Max von Laue discovered that X-rays were diffracted by crystals in 1912. That same year, William Lawrence Bragg and his father William Henry Bragg developed Bragg's law, which related the observed diffraction patterns to the interplanar spacing in crystals. When an X-ray hits an atom, its electrons absorb the energy, then emit another X-ray with the same energy in a process called elastic scattering. In a crystal, atoms are spaced into regular arrangements on planes separated by distance d, which is the same order of magnitude as the entering radiation's wavelength. X-rays are scattered by these evenly spaced atoms. When the angle between the incident and scattered X-ray beams reaches a certain value, constructive interference occurs and the signal is amplified. Bragg notated this mathematical relationship as 2d sine theta equals n times lambda. With the theory behind it figured out, interest in this new form of material characterization quickly grew. X-ray diffraction can give information about the size and spacing of atoms in a molecule, as well as shed light on the electronic and mechanical properties of a material. By analyzing the angle and intensity of scattered X-rays, a 3D image of the molecule's electron density, and therefore structure, can be gained. The first crystal structure, of table salt, was confirmed in 1914, followed by the first biomolecule, cholesterol, elucidated by Dorothy Hodgkin in 1937, and the first protein, myoglobin, confirmed by John Kendrew in 1958. Today, hundreds of thousands of protein structures have been uploaded to online databases, and computational tools can bolster the ease and speed of the analysis process. Modern X-ray diffraction data is collected by generating X-rays, filtering the produced radiation, bombarding the sample, recording the diffraction patterns, and then converting them to electrical pulses using a transducer. X-rays can be generated by radioactive sources, synchrotrons, or particle accelerators, but in research labs it's most common to use an X-ray tube. In an X-ray tube, electrons are generated from a hot tungsten filament, then accelerated with high voltages towards a copper plate embedded in a rotating anode. This process is highly inefficient. 99% of the energy is transferred to heat, and the setup must be cooled during use to ensure proper data collection. Next, the generated X-rays might be passed through a filter to remove unwanted spectral lines and reduce background noise. These filters are typically made of zirconium or silicon and help improve the resolution with which structures can be determined. The filtered X-rays then arrive at the sample, which is a carefully grown crystal of the material. As the crystal is rotated, the angles and intensities of diffraction are recorded, as is the orientation of the crystal itself. The diffracted X-rays travel to a transducer, which converts radiant energy into electricity through a photon counting method. Transducers can be gas-filled, Geiger tubes, or semiconductors, but the most common are scintillation counters, which take advantage of the luminescence produced when radiation strikes a phosphor. These flashes of light are transmitted to a photomultiplier tube and converted to counted electrical pulses. The number of photons per flash is proportional to the energy of the incoming radiation, so the beam's intensity can be determined. The intensity is then plotted against the angle of the beam to produce characteristic peaks. This can be compared to a database to qualitatively determine the composition of a material, or it can be transformed mathematically to give quantities like the interplanar spacing, spatial coordinates, or percent crystallinity. X-ray diffraction is a powerful tool for characterizing materials. Though XRD doesn't allow for the study of time-resolved information, and it can be difficult or impossible to crystallize compounds, it still offers many insights on the structures and properties of important molecules across all areas of chemistry, engineering, and biology. XRD has allowed for the fingerprinting and easy identification of everything from pharmaceuticals to geological formations, textiles in forensic cases, and even DNA.